to get the students and faculty member to listen and interact. So okay, okay. So I think this goes a long way in tradition, and I'm thankful that you could join us for the entire week here at TIFR. And I would let Professor Gagan Mohanty introduce Professor Wilkinson to everyone in TIFR. So.
Thank you. So yes, indeed, it's a pleasure to introduce the speaker, the colloquium speaker for the day, Professor Guy Wilkinson, FRS from University of Oxford. So Guy is an international adjunct faculty of our department, and through just to give a flavor of his academic accomplishment and the different kind of experiment he has been working on. So starting with this Delphi experiment at Large Electron Positron Collider, where he played a major role in so-called energy calibration using this resonance polarization technique that was very crucial for many of the physics result that came out of LEP. So he was the convener of that energy calibration group, and he was one of the founding member of this Large Hadron Collider Beauty, or LSCB experiment, and he was spokesperson, so-called the intellectual leader of that experiment for several years. And so right now he's pushing, he's heavily involved with the LSCB upgrade, and also trying to push this next, while the LSC is taking data, the community, high energy physics community, looking for the sort of collider after LSC, and in that connection, the so-called future circular collider, particularly the E plus E minus collider, FCC-EE. So he has got many awards. Some of the, other than being an elected member of the Fellow of Royal Society, he has also got this James Chadwick Medal and that IOP award for his outstanding contribution to the experimental flavor physics. So without any further ado, so I would request Guy to come up.
Okay, I hope you can hear me. Good. So thank you for that very kind invitation, introduction, and thank you for your hospitality here. I've been here actually since the start of last week, and I've eaten very well, but Gagan's worked me hard. I think this is the 6th talk I've given. So those of you who have been in several of these, I apologize. Right, so I'm going to talk about the search for new physics in the age of flavor, and I'm going to start with a prologue. I'm going to take you back to 1964. So I wasn't around then, and I think most of the audience were not around then, but we have a good idea of the things that happened, a very dramatic year. But in the area of physics, there were also important things that occurred. 2 important things which are very relevant for this talk. Firstly, there was the discovery of CP violation, which is the difference in behavior between matter and antimatter. This was discovered in the kaon system, and I'll come back to this. This led to the Nobel Prize being awarded to a couple of the authors in 1980. Also, by coincidence, this was the year that the quark model was proposed. The quarks we now understand to be the most fundamental building blocks of hadrons. So this was proposed simultaneously by Gell-Mann and George Zweig. Gell-Mann was awarded the Nobel Prize in 1969. Zweig wasn't. If you want to know more about that, we can discuss over coffee. So these are 2 very important happenings, and I think we haven't yet got to the bottom of these. We have a lot to learn. So let me come to the outline of the talk proper. I'm going to be talking about flavor, and so this is a rather whimsical word, so I will try and, I'm aware this is a colloquium, so I'm going to try and pitch these introductory slides at the appropriate level. I'll be talking about one experiment which is very, very good for doing this physics. My experiment, the LHCb experiment. So this is one of the 4 experiments at the LHC. And I will then show rather briefly just 2 or 3 selected results from this experiment. And I will finish by looking to the future. Okay, so the standard model As I hope most of you know, this is a quantum field theory that describes the fundamental particles plus the electromagnetic weak and strong interactions. All tests made of this standard model, in particle colliders at least, have been fully successful. And the most spectacular recent example was the discovery of the Higgs boson, now 11 years ago. But one very important part of this theory you often hear less about, but I think it's absolutely central, is the flavor sector and its associated physics. So in particle physics, the concept of flavor relates to the existence of different families of quarks and how they couple to each other. So we know that there are 6 flavors of quarks grouped in 3 generations. And these quarks have a very distinctive hierarchy in mass. The up and down quark weigh essentially nothing, but then you go up to the top quark, which weighs pretty much the same as the nucleus of gold. So this immediately provokes the question, why are there 3 generations? Why do the quarks exhibit this striking hierarchy of mass? And to these questions, we don't yet have the answers. And these are questions of flavor. The questions of flavor also extend to the lepton sector, the other class of fundamental particles. Again, we have 3 generations with a charged lepton and a neutrino within each generation. And the charged leptons, again, exhibit this striking hierarchy of mass. The electron, the muon, which is essentially just a copy of the electron, but 200 times heavier, and then the tau. Probably this is a good point just to remind you of something that I would imagine most of you know, but the quarks, we cannot study these in isolation. But because of the nature of the strong force, the quarks are always bound together inside bigger objects, which we call hadrons. So we have 2 sorts of hadrons, spin half hadrons called baryons, which are in their most simple form made up of 3 quarks, and then mesons, which are made of a quark and an antiquark. Okay. Now, why the strong force requires these distinctive groupings, 3 quarks or a quark and an antiquark, this is understood. But what is curious is that other patterns are permitted, but these have proved very, very difficult to find over many decades of searching. This is a question of the strong force rather than a question of flavor, but experimentally it can be equally well addressed by a flavor experiment. And I will come back to this later. So I've talked about the hierarchy of masses. There's another distinctive hierarchy we see in nature. And that's in the standard model, the quarks can only change flavor through the emission of a W boson. And these are snippets of Feynman diagrams. So you see a top quark changing to a bottom quark emitting a W, or it can change to a strange quark or a down quark. And at each of these vertices, there is a coupling constant, which is an element of a matrix. And this is the so-called Kabibo-Kobayashi-Mascara matrix. It's a 3 by 3 matrix because we have 3 generations. But what is interesting is that if the quark is changing to a quark within its generation, here a top quark to a bottom quark, the bottom quark is within the same generation, then the coupling constant is very, very close to 1. If it's changing something outside the generation, the coupling constant is much, much smaller. So in the elements of this matrix, you again have a very distinctive hierarchy. And this is presumably trying to tell us something. It's another puzzle of flavor, but what it's telling us, we have not yet understood. This matrix is also linked to another big puzzle of flavor physics. And this is this matter of CP violation, which, as I said, was discovered almost 60 years ago. Now, I won't, in the time we have, formally define what the operation of CP is, though it's not very complex. But the violation of this can be understood as that we see a difference in behavior between matter and antimatter. And it was a great surprise when this was first observed. It was first observed as a rather small effect involving kaons. Now, in the standard model, this CP violation can be accommodated, but not explained by an attribute of this matrix I've just shown you. The attribute is an imaginary phase of that matrix. But if we have any physics which is beyond the standard model, new physics we've not understood yet, that could in principle have its own CP violation, which would behave in a different way. Now, the CP violation in the kaon sector, as I said, is very small, but it was known even before experiments were made that in B quark decays, bottom or beauty quark decays, much larger CP violating effects are expected. But the opportunities to explore these remained limited until colliders arrived that could make lots of B hadrons. Now, CP violation has cosmological connections. So the great physicist and Russian dissident Andrei Sakharov proposed 3 conditions which were necessary for baryogenesis to enable the universe we have around us to come into being. In particular, that the universe be made of matter rather than the antimatter and matter, which were created in equal amounts in the Big Bang. And one of these conditions was the requirement of CP violation. But the amount and nature of CP violation that is required for baryogenesis is very, very different from that we have in the standard model. So presumably there's some new physics out there with its own CP violation, which is driving this. We're told we understand the mass hierarchy. I would dispute that. If we do, I would be very impressed. Okay. So this standard model has problems. We've already encountered the following shortcomings. We have no explanation for baryogenesis. We can't explain, I insist, the quark mass or CKM hierarchy. And we have no real explanation for CP violation. And there's lots of other examples: dark matter, dark energy, neutrino mass, gravity. Why is the Higgs boson light? So there are more ambitious theories out there, for instance, supersymmetry, that can solve at least some of these problems. And these theories generally predict new particles or effects outside the standard model. And the goal of the LHC is to search for evidence of this new physics.
Okay. There's a question in between. Sorry about that. Professor Wilkinson. TP, you can ask your question.
Yeah, could you kindly go back to the previous slide? Yeah, I'm sorry, I cannot agree with the second statement. No explanation for the quark mass or CKM hierarchy. There is recent work from me and my collaborators which answers precisely these questions, and I have linked both the papers in the chat. They are in the archive. Kindly do have a look, please.
I will have a look. Maybe what I should have said is that there have been many explanations proposed, but no single unique explanation, and no explanation which has been, I would say, experimentally tested or accepted. But I shall look at your papers.
Yeah, please continue. TP, let's discuss this later, okay?
Yeah, thank you. Thank you.
Yeah, thank you.
Okay.
Yeah.
Right. So we want to find this new physics, and there's basically 2 strategies we can approach, and this is what we're doing at the LHC. There's the new physics is behind the walls of the standard model fortress, and we need to get behind those walls. So we can approach in a very brute force manner, which means trying to raise the energy as high as possible and make new physics particles on shell. Or we can be more devious, more cunning, and we can make precise measurements of processes in which the new physics particles enter through virtual loops. Now, both methods are powerful. LHCb specializes mostly in this approach, and those of you with a classical education will know in this case which was successful. Okay, so just to explain a bit more how with this indirect approach we are sensitive. So this can be done with all sorts of hadrons or bosons, but with beauty hadrons containing beauty quarks, and here I show examples, are particularly good for this. But here you see again Feynman diagrams, as I showed earlier, but these are rather complex Feynman diagrams with their suppressed processes with loops. And these loops involve virtual particles, often very massive particles like the top quark or the W boson. But these are the standard model particles. In principle, contributing to these amplitudes, you also have new physics particles if they are there. So the idea is to make very precise measurements of these processes, compare them with the standard model theory, and see if we can find inconsistencies which point to the contribution of these new heavy particles. So to recap, we're trying to probe an area of the standard model where there are many unanswered questions, and we're looking for the contribution of new massive particles. And a very good way to do this is to produce beauty quarks. They're very good for CP violation. They're very sensitive to these virtual loops. And as a bonus, we can also make nice studies of how quarks are bound together in the hadrons. So how do we make beauty? Well, you need to go to a collider which produces them in sufficient quantities. And we've been getting progressively better and better at this. So in the 1990s at LEP, we could produce about 1 million per year. But now at the LHC, we can produce of the order of 100 billion, even 1,000 billion per year. So the LHC, as well as being a machine for producing Higgs bosons and maybe exotic new heavy particles, it also happens to be a beauty factory. And LHCb is a dedicated experiment to exploit fully this rich resource. Hello, yes.
I'm sorry, just a very naive question. You said that beauty quark was sensitive to these things. So could you just explain why is it so? Why not other flavors of quarks?
Right, yeah, no, it's two things, right? So the fact that beauty manifests higher CP violation, this is compared to like kaons, this is a subtle point, but it's because it's in the third generation and it can couple to the second and first generation. It just turns out, if you do the maths, that you get bigger effects there, as I will show you. Secondly, the beauty quark, because it's heavy, it can decay in, the hadrons can decay in hundreds and hundreds of ways. And, you know, the PDG is full of them, and that gives you a huge number of observables to look at. Well, one other thing is that because it's quite a heavy hadron, the QCD effects can be calculated quite well. Therefore, the predictions are rather clean. Good question. Right, so this experiment here. So this is a big experiment, but compared to CMS, it's not enormous. It has about 1,600 members from almost 100 institutes. And its goal, as you see in the title, is to look for, is to actually study beauty and indeed charm quarks and look for physics beyond the standard model. So here is LHCb, one of the 4 experiments, this one actually close to Geneva Airport. You could actually see it when you get off the plane if you know where to look. I should also, Atlas and CMS, these experiments have very rightly received most of the publicity from the LHC, from the Higgs discovery. And I should mention, because CMS is an experiment that TIFR are contributing greatly to, this does have impressive capabilities in flavor physics, but it's a more general purpose experiment. LHCb is a dedicated flavor experiment. So let's try, I want to now, for the next portion of the talk, try and explain what properties this experiment needs, and I'll show you its, so I'll step through these. Firstly, it needs an optimal geometry. The B hadrons are predominantly produced forward and backwards. Therefore, the best place to build the detector is like forwards. This is to be contrasted with CMS, which you see as a more barrel-like construction. Also, I'm going to be flashing up various decay chains, all starting with a B meson. And if you don't know what these particles are, I apologize, they're not necessary for the discussion, but what you should know is that we don't actually see the B meson itself, we see its decay products. And so we need to be able to reconstruct the decay products and build backwards to see what the parent meson was which decayed. So we need to know what the daughter particles are and where they came from. This is very important. Finally, what's important, the final point is that when these collisions happen in the LHC, not every one contains a beauty hadron. And indeed, not all beauty hadron decays are of interest. So you need to select quickly the ones which are of interest, and this requires triggering, which is a very important concept in hadron colliders. So this is the shape of this is a schematic of the experiment. I should actually say this no longer exists. It's now being replaced by an upgraded one, which we're commissioning now. But the upgraded experiment superficially looks very, very similar. Here is where the proton-proton collisions occur. So if the B hadrons are produced, some will go backwards. We won't see those. We don't have enough money to instrument that region of phase space. But the ones which are produced in this direction, we will see in this spectrometer. So this is about 18 meters long. Okay. So stepping through around the actual interaction point itself, there is an exquisite detector, a silicon detector called the vertex locator, or VALO. So this comes in two halves. This is half of the VALO in the lab. But these approach very, very close to the beamline. They get closer than any other detector in the LHC. They get within 8 millimeters of the proton beams. And that's because you're wanting to reconstruct the vertices of the B decay as well as possible. The B is produced in the primary interaction. Here you see other tracks, which are just junk being produced from the proton collision. But this B is produced, and it's a neutral B. And this has a distinctive lifetime, and it will fly a distance of about 1 centimeter before it's self-decaying. So you see you'll get tracks here, just 2 tracks, which come from the B decay, which will be displaced from the primary interaction. So you need to be able to reconstruct this vertex and this vertex as well as possible. You also have Cherenkov detectors. You know about Cherenkov radiation, maybe. So a charged particle which moves faster than light in a particular medium, and here we have fluorocarbon gases. We have 2 Cherenkov detectors. It will emit a cone of radiation at a distinctive angle related to the velocity of that particle. So if you know the momentum of the particle, and we can measure that, we can get the mass of the particle. So here you see the angle against momentum, and you see these different particle species. So the idea is to image this radiation, and therefore you'll be able to tell whether the particle was a pion or a kaon or a proton. Here are the mirrors which the radiation are reflected off, and then they are imaged in these photodetectors. And then you have a magnet. The charged particles go through a dipole magnet, and this bends them so we can learn what the charge was and also what the momentum of the particles were. And then we have calorimetry and muon systems, which we need not discuss more. So I talked about this trigger, and I just want to emphasize what a big challenge this is at the LHC, not just for LHCb, but also for CMS. Yes, of course.
Still wondering about that rich, the thing that you showed. Yeah, you showed proton tracks, and I'm wondering where you got such energetic protons from. Is that from jets, or?
They can be produced in the primary interaction. These are of 20, 30 GeV, or they can be produced in B decay. Yes, or in B decays, if a lambda B is produced, that can eventually decay to a proton, or the primary. So you get strange baryons produced, which will decay. Yeah. Okay. So I just want to emphasize the challenge of dealing with this data. I mean, it's the LHC, there are collisions at a rate of 40 megahertz, and it operates for like 15% of the year. Our raw data size is something like 100 kilobytes, so that's 15,000 petabytes per year. That's less than dealt with by search engines, but if you compare with Facebook at least a year or two ago, that's more than Facebook deals with. So this is the data, schematically, the data of LHCb and Facebook. But if you look at our financial resources, Facebook has more than us. So we can't just read this out, store it. It also take forever to analyze it. So we want to decide very quickly whether the interaction was of interest or not, and just keep for further analysis those which are potentially interesting. So there's various strategies which one can use. We're looking for B decays. So for example, firstly, you need a very simple signature which you can exercise in hardware very, very quickly. So what we do here, we know the B is quite a heavy object, and so it will tend to, the things it decays into will tend to have a characteristic momentum, and in this direction we look for a transverse momentum or a transverse energy which is characteristic of the B decay. So we can do that in the muon chambers or the calorimeters. Then we use that signature to throw away things which are obviously background, but then we have a bit more time to play with, then we can actually reconstruct some of these tracks. And with an individual track, with this vertex detector, we can, if we reconstruct it back to the beamline, we see that it will be in general displaced from the primary interaction region. And that's because the beam meson has flown this characteristic distance of 1 centimeter. So we are looking for these sort of impact parameters. And then if we have more time, we can reconstruct all the tracks and try and see if some of these tracks indeed come from a vertex in space, which would be the actual B decay vertex. So each successive step provides improved discrimination, but it needs more information and time to execute. So let us not dwell on this, but the point is we start with 40 megahertz, but in the end, we're writing out something like 12.5 kilohertz of events. And the key point is that in contrast to the CMS experiment or the Atlas experiment, which are very interested in Higgs and supersymmetry, we are mostly interested in flavor physics. So this trigger can be, the bandwidth can be entirely devoted to looking for these heavy flavor decays. So what I'm going to show you now are some results from runs 1 and run 2 of the LHC. We are now embarked in run 3. So in terms of the amount of data we've collected, particle physicists express it in terms of integrated luminosity. This is 9 inverse femtobarns. Let's not worry about that. What it means in terms of Bs is that something like 10 to the 12 B anti-B pairs were produced within LHCb within this data set. So a very big number. Right, so we have limited time and I don't want to overstay my welcome. So far, we've published about almost 700 papers, but I'm going to just give you a flavor, if you excuse the pun, touching on 3 topics. I just have about a couple of slides on each topic. Firstly, CP violation, then talking about this mystery of how things are bound together in hadrons, and finally, probing for new physics in suppressed decays. So CP violation, to recap, somehow this is our main raison d'etre to understand something about the difference in behavior between matter and antimatter. I explained how in a standard model, this can be accommodated by a complex phase in this matrix. Now, this matrix is unitary, and you can therefore write down certain mathematical relations, and those relations can be expressed geometrically in the complex plane. So this sounds very involved, but what it means is that if the standard model is right, then you can actually write down triangles, and the parameters of these triangles are related to the parameters of this matrix. And you can measure the size and angles of these triangles in beauty decays, and they tell you things about the matrix. And in particular, the fact that the triangle has a finite area and it has angles, these angles are related to CP violation. And this angle here in this corner, which we call gamma, is related very, very directly to this unique phase of the matrix. Now, the value of this angle can obviously be predicted if you know the other parameters of the triangle. It's just the cosine rule, et cetera, et cetera. And some of these other parameters we measure well. So there is a very good prediction of what this angle should be. But you can also then go to an actual CP violating process and measure this angle itself directly. And it's a very important and non-trivial exercise to compare your direct measurement of this angle with the prediction of the angle. Because if there's other things contributing to this matrix you don't know about, then this triangle may not close, and there may be other things going on, which would lead to inconsistencies between these two determinations of gamma, which would point towards new physics. For instance, a 4th generation of quarks or supersymmetric particles. So how do we measure this angle? So it's this angle, it relates to a phase in the matrix, and it's a hidden phase. So if you have it's a phase in the amplitude, and to get a probability in quantum mechanics, you must square the amplitude. So if you just have a single amplitude and you square that, then you lose all sensitivity to the phase. What you need are 2 amplitudes, or two different decay paths. You can think of this in terms of the double slit experiment, that if you have two paths, then you can get interference between these two paths. So here are two possible decay modes. And again, if you're not familiar with these particle nomenclatures, don't worry. But there's here, this is a B meson going to a D meson, which contains a charm quark and a charged kaon. And here going to a anti-charm meson and a charged kaon. Now you want these to interfere, and you can make them interfere if you can reconstruct the charm meson or the anti-charm meson in a decay mode which is common to both of them. So that is akin to saying that you don't know which slit the light went through. If you do that, you expect interference effects. Now these interference effects will be different between B plus and B minus because this phase is CP violating, and it actually changes sign if you change the if you look at this decay mode here and change the B minus to a B plus and the K minus to a K plus, that will give a different interference pattern. At least this is what we expect. So let's see this in action. So these are the two decays, and now we're going to reconstruct this. This is with LHCb data, where the D has decayed itself to a kaon and a pion, but with a particular charge configuration. And this charge configuration is so picked here that you're essentially, though there are two paths contributing, one of these paths is very much favored. It's like, you know, the light is, almost all of the light is going through one slit. So in this case, you don't expect very much interference. And so far, this is what you see. So this is a histogram of the invariant mass of B decays of this sort. So this peak here is the signal. Your eyes might be drawn to this, but ignore it. This is background from other decays. And what you see is this signal is pretty much the same height if you look at a B minus decay or a B plus decay, when you swap the charges of everything. So this is telling you here you see no CP violation of note. And this is as expected, because you're looking at a case where essentially only one path is dominating. Now we can change the charge configuration and then look at a different path and to a case where we now know that the contribution from the two paths are pretty much of the same size. There you expect large interference effects, and you expect a big difference between B minus and B plus. And this is what you see. See, this peak is enormously large compared to this peak. So this is a very suppressed process. You need a huge number of B decays to access this. But what you're seeing now, this is difference in behavior between matter and antimatter, an effect which was tiny in the kaon system, but greatly amplitude here with the Bs. And if we measure this asymmetry, we can get very clean access to gamma. So we have done this. So I said that we knew that what this gamma is as predicted by the other parameters of the triangle. We are now measuring it precisely. We're not measuring it as precisely as the indirect prediction, but we're doing very well. We're doing about 5 times better than when the LHC turned on. And our precision is about 4 times worse than that of the actual prediction. The gamma we measure is now lining up at present quite well with the predicted value, but we would like to improve this measurement so that we can really get down to the same level of precision as the prediction. And then we'll make a very, very sensitive test of this very important sector of fundamental physics. So this is what we aim to do, and with the plans for our experiment, we think we can get there. Let me now switch to coming back to this question of quarks being bound within hadrons. So I talked about baryons with 3 quarks and a meson and which are made of a quark and an antiquark. Why do you have these distinctive patterns? Well, it's because the quarks have colors, and this is another whimsical word, but this is like the charge of the strong interaction. You have 3 colors, which we call red, green, and blue, and overall objects must be colorless. They must be white. So red, green, and blue in a baryon will give you a colorless object, as will blue and anti-blue. I don't know how to draw anti-blue, so I've just drawn it as cyan there. So that explains this structure. But you might imagine, you should, those of you who are thinking about this will immediately realize, as Gell-Mann did almost 60 years ago, that you can make colorless objects in different ways. For instance, I could have tetraquark made of a quark, antiquark, and antiquark, or a pentaquark made of 4 quarks and an antiquark. With those color combinations, I can construct these objects. So Gell-Mann said they should be out there, and people started to look for them, and they looked and they looked and they looked and they looked for over 35 years before any candidates which have withstood scrutiny were actually found. And the LHC has played a big role here. You might say, what has been discovered at the LHC? And you'll say the Higgs. It's not just the Higgs. There have been 71 other particles discovered at the LHC. And these are all hadrons, and many of them are exotic hadrons, meaning that they fall into these sorts of categories. And trying to understand, why they are of the nature they are and why they take the masses they do, this will tell us more about how the strong interaction works at these energies. And indeed, there's a community which is fascinated by this. The LHCb and indeed the Bell experiment, a previous flavor experiment, they were both designed to discover and measure CP violation, but in both cases, their top cited paper, 2,300, 1,600, are actual papers to do with studies of these exotic hadrons. There are theorists who are obsessed by this. And not just theorists, the wider world seems to be very interested in these things as well. Each time one finds one of these things, this is a collection of newspaper clippings related to what looks like a very esoteric study, but it was an important study. And some of these are very excitable. I think this came from Iran, opening the gates of hell. What they were on about, I don't know. And even this work has inspired pieces of music. That same measurement inspired this saxophone quartet, which was played in the Montreux Jazz Festival. You can find this on YouTube. So we don't have time to talk you through all these. I'm just going to say a couple of words about these discoveries here, which are pentaquarks. So the hunt for pentaquarks, this means hadrons with 5 quarks in them. This is a long journey, and it's had some rather ignominious cul-de-sacs in history. For example, in the early 2000s, a group of experiments, these were just experiments which access lighter quarks, not beauty quarks. One of these experiments seemed to find a peak which consistent with the pentaquark. Another experiment confirmed that, a third did, a fourth did. But then a more sensitive experiment came along and saw nothing. And these other experiments had to sheepishly agree that indeed there was nothing there. So this means that this search for pentaquarks is a checkered history. This particular episode here has been written up by this gentleman who rather kindly calls it a curious history in the history of science. So if you think you see a pentaquark, you have to be very sure. Okay, so LHCb a few years ago looked at a decay of a so-called lambda B baryon to a J psi proton and a kaon. So this is a 3-particle decay. This is the mass peak it found. You see it's very clean, very little background. This was done actually just for CP violation studies, but somebody made the plot of the invariant mass of the J psi and the proton. So looking at if you put the J psi and proton together, what is the relativistic invariant mass? And one sees this very distinctive peak here. This is in black. Just concentrate on the black. So what this is telling you is that this is indicating that there seems to be a short-lived particle which existed between the decay of the lambda B and the production of these particles. And this short-lived particle decayed into a J psi and a proton. And if you know the quark makeup of the J psi and the proton, the only way to explain this is that this particle had 5 quarks in it. So this is dramatic. But you need to be very, very sure. So you need to make studies, for example, of you need to say, okay, let's say we know nothing about pentaquarks, but let's try and fit our data to all known other particles which exist in the particle data group Bible. And this is what this red is here. And you see that this fit does not explain the data at all. So you're drawn to the conclusion that you have to allow for the existence of this exotic particle, this pentaquark. And if you do this, you can fit the data very well, and you get this single state here. And rather curiously, the fit wants another state down there, which is not evident to the eye, but that's how fits work. So the data here favors very clearly this pentaquark and maybe one others. But this is not the end of the story. So this was done with the first tranche of data from LHCb. And this next plot makes clear why more data matters. So this is the particle physics equivalent of just getting a better telescope and looking more precisely at a distant galaxy. This is what we had initially. Now you add essentially 10 times more data, and you see other features are coming out. So there seems to be something here. There was evidence of it there, but there it just looked like a fluctuation. And indeed, if you look in this region, you see that there's more going on. So you have, this is this peak I spoke about, this new peak. And in this region, there's not just a single pentaquark, but there's just 2 pentaquarks there. So this data favors 3 narrow states, each of which are pentaquarks. And that rather unconvincing broad state, which was fitted to the initial analysis, is no longer there. So this is great, but just to stop here would be stamp collecting. We actually need to know more about these states. We would like to measure their spin and parity and to understand why they have the masses they do, because this will tell us, why and how hadrons are bound together and why it's been so difficult to find these pentaquarks and tetraquarks until now. For example, you might say, well, in this pentaquark, you could imagine the 5 quarks are tightly bound together. That's a possibility. Or they could be more molecular-like. You could have 3 bound together, like in a conventional baryon, and then the quark and the anti-quark sort of loosely bound to that by some molecular-like van der Waals force. So there's theories on the market which are, and many which posit both of these possibilities, and they make predictions, and we need to make more measurements with more data to actually try and work out which of these is correct. And by doing so, we'll learn more about hadronic physics. For those of you who know about the pentaquarks, I just flag up, you may have missed this last year, we've now found a new pentaquark in a different system. This is a CC bar UDS pentaquark. So these things are now popping up with some frequency. Okay, so my final example is now coming back to pure flavor physics and looking at this idea of using suppressed decays as a probe of new physics. So these are Feynman diagrams, but they have these loops in, and I emphasized earlier, if you have a diagram with these loops, these are virtual particles, and they are very sensitive to the possibility of new heavy particles running around these loops. So making precise measurements here is valuable. And a particularly valuable process is when the beauty meson decays to a strange meson and 2 leptons. And the poster child, and there's many realizations of this, but the poster child is where a B decays to what's called a K star, that's an excited kaon, that decays to a kaon and a pion, which you detect. And you also detect 2 leptons, like 2 muons. And this is a very rich system because you can measure decay rates, but you can also measure all the angles involved in this decay. And these angles are access variables and observables, which can be precisely predicted and also perturbed by new physics. So here is an example of the actual measurement of the rate, the cross section. But this cross section here is shown in different bins. This is the invariant mass of the dilepton system. Because the physics varies with this variable, the plots you see are always shown as a function of the invariant mass of this system, the Q squared. Okay, so the data points here are, that's the data, and the blue is the prediction from the theory, and it has some extent on it because the theory prediction is not exact because of the difficulty of the hadronic physics involved. But what you do see is that there's a tendency for the data to be lower than the prediction. And this is intriguing. And this leads you to look at other decays of exactly the same sort. And here you are all again plotted against Q squared. And you see in all cases that the data is lying underneath the prediction. So this is extremely intriguing. but you will note that the theory uncertainties are significant. So therefore, there's a motivation to try and look at some of these other variables and observables you can measure in this process, where the theory prediction should be on a more robust footing. And and you can access these variables by reconstructing the decay and fitting the kinematics of the final state. There's many things you can look at, and I'm afraid the nomenclature is very, very boring. So this is the most exciting plot I can show you, and it's called P5 prime. But this P5 prime has excited interest for over 10 years because it's supposed to be rather well predicted. The predictions are here in orange, but you see that the measurements are significantly high, almost 3 sigma in both of these bins. And this is just one example. So this is one reason why people really think there's something going on in these decays. And until recently, if I was giving this talk last year, this slide would be the triumphant conclusion, where we found something that seemed to categorically show that something was really deeply amiss. What this is a lepton universality test, where you look at these decays, but not just for the muon case, you also look for when it decays into electrons. In the standard model, the gauge bosons couple to electrons and muons equally. This is lepton universality. So all we're doing here is measuring in some region of kinematics, the ratio of the number of times the muon decays occur to the electron decays. And you would expect this to be unity. And this has been measured for 2 classes of decay, the B to K star LL, and here we call the ratio RK star. And for the case where B goes directly to a non-excited kaon LL, we call this RK. And you see in both cases, the measurements are well below 1 at almost the 3 sigma level. So this picked up a very large amount of interest. So it's rather, I have to be rather sheepish in saying that in the end, science wins out. And these data have been reanalyzed in a better way, and this new analysis has discovered a previously underestimated background. So this is a publication from earlier this year. So I've taken the plot and I've rotated it so it's consistent with this. So the standard model here is at 1, rather than having 2 points. There are 4, because for each of these processes, a measurement has been made in 2 kinematic regions. But these are just details. What you see is that this is lining up with 1. So the bottom line is lepton universality holds. So the moral with science is that the truth will out. But the earlier anomalies I showed you, the earlier puzzles, they remain. But the explanation in terms of lepton universality failing, that seems to not be in play anymore. At least I thought that, but 1 month ago, a sister experiment, the Bell 2 experiment, which TIFR are involved in, they released the first results for this decay. It's again a decay of the same family, a B decaying into a strange quark and 2 leptons, but here the leptons are neutral leptons, they are neutrinos. So this is actually very difficult for us to look at LHCb. But what is interesting, this is seen for the first time, but the rate at which it's seen is almost 3 sigma above the standard model prediction. So this adds to the mystery, it adds, the plot is thickening. So in all these studies, what we need is more data, better measurements, and in some cases, better theory predictions. So stay tuned. Right, so before finishing, I just want to show you a couple of slides giving the path forward in this area of physics. So firstly, this LHCb experiment, it has been upgraded. Why do you want to upgrade? Well, you want to improve your precision, and precision means more data. Higher precision will give you higher sensitivity to new physics. So a rule of thumb is to double your sensitivity, you need something like 4 times more data. Now, the results I've shown you have come from 5 years of operation, and with the intermediate shutdowns, that's like 8 years of 8 years of time. So to double the precision with the current experiment, you would need 20 years. and with more shutdowns, that will go up to three decades. Now, this isn't very good for students, so you need a better plan. So you need to improve the efficiency of the experiment and the rate in which data is collected. So here is, this is the data we collected, original LHCb. This red here, if you focus on that, this is essentially proportional to the amount of data we expect to take. So we've taken this much data. We are now, over the next 10 years, in the period of LHCb upgrade 1. And beyond that, we are planning an LHCb upgrade 2. And you see, the idea is to increase the amount of data by a very significant amount. And without going into great details, this is done by going back to this trigger and doing something revolutionary, which is to actually remove the first level of the trigger, which is done in hardware, and to try and read our whole detector out at 40 megahertz. This involves a huge amount of data throughput, and then try and execute very sophisticated trigger algorithms in software only. And if we can do this successfully, we can also run at higher luminosity, which means running at higher brightness of the beams and collecting more data. So we will, over the next 10 years, we will collect data about 10 times more quickly than previously. And then beyond that, we hope to do this again, but increasing still more the luminosity of the beams at the LHCb interaction point. What I should say, with respect to my colleagues here, LHCb is not the only experiment in town. There's the Bell 2 experiment in Japan. This works in a very different environment, but it's a dedicated flavor physics detector. It's very much getting into its stride. It's now accumulated about as much data as the original B factory experiments, which operated in 2000s. And it's hoping to increase this by an order of magnitude in the coming 4 or 5 years. And I remind you, it's this experiment which gave that very intriguing result for B to K nu bar. And in the very further future, I spoke about this to some colleagues earlier this morning, a feasibility study is now underway to build a super collider at CERN, a 91-kilometer tunnel, which would house a E+ E- collider of unparalleled physics reach in many areas of physics, including flavor physics. And this tunnel could then be reused as a hadron machine, and the same message would apply. So these are rich prospects indeed. So to conclude, I think flavor physics is important because it addresses many of the open questions of the standard model, and it's intrinsically very sensitive to any new physics that lies beyond. Great progress is being made. I've trumped my own experiment, but there's been exciting progress in studies of CP violation, in discovering new exotic hadronic states, and probing for discrepancies with the standard model in suppressed decays. And this program is ongoing, and the future looks bright. So I think we are truly living through a golden age of flavor. So thank you for your attention.
Okay, thank you once again. There's a question there first. Let me take that.
Okay, great talk. I would like to know that you're planning in the future to remove the first layer of the trigger, right?
Yes.
How exactly are you planning to store the data? I mean, that would be huge, right? Compared to what is currently being generated.
Right. So thank you. So you obviously know about triggering. So we remove this. So this means indeed the data flows through. It gets read out at 40 megahertz. But then we deploy actually in GPUs, graphical processor units. We employ, we actually, we reconstruct tracks in the vertex detector and look for impact parameters. And we exert a level of suppression then. So that level of suppression is, I can't remember, it's over a factor of 100. Then what we do is we actually write the data out onto disk, but not a permanent disk. We put it onto disk, and we can store data on this disk. We can collect data for up to 2 weeks of running. But we then make sure our detector is fully calibrated, and then we run the second stage of the trigger, sometimes 2 weeks after data taking, on that collected data, but with the full calibration, such that we essentially running the final offline like algorithms with full calibration on that buffered data, and then we store it to disk. It's not actually disk rate, but it's similar to that. So what we actually finally store to permanent disk is not so different to what we've been doing until now. Okay.
Okay. Questions? More questions? Yes.
Hi guys. It's a very nice talk and exciting results from LSCB, and you also reported one of the decay mode of Bell. So I just wanted to know whether LSCB also has a sensitivity to that decay mode to make independent measurement.
The answer is no. So this is so the reason is very clear. So this is beta K nu bar. So that's a neutrino. So we don't see that neutrino. Bell doesn't see that neutrino, but in Bell, there's the only things which are produced in Bell is a B and an anti-B. So it's a very simple environment. So even though you don't see the neutrino, I mean, for example, this isn't the only way they do it. You can reconstruct all the other tracks in the event, and you know precisely how much energy you have lost, and you can see if that's consistent with 2 neutrinos. So there's in Bell 2, it's not straightforward, but there's a good and obvious ways in which you can isolate these decays. In the LHC, it's impossible because you have hundreds, thousands of tracks, and all that would come out would be a single charge kaon. So trying to isolate this rare decay from all that mess is pretty much impossible. So we leave this to Bell 2.
You could pass to Shubham.
Hi, very nice talk. I have a question regarding the kind of data analysis techniques which are used in LSV. So like when you're looking for new physics, one of the main challenges we often end up in understanding what is physics and what is not, or possibly some systematics. So are there any efforts in LSC to understand like kind of blinded data analysis, or do you do such procedures to understand that signatures which you're actually measuring is truly physical effects or not coming from your background?
All the analyses which are looking specifically for new effects, any analysis which is not really mundane is always done in a blinded way, and that's been done right from the start. So you know, so in trying to like measure things like that, nobody knows what the answer is until the final stage of the internal review. So we're very careful in that manner, but it doesn't always. But still, it doesn't. It's not a panacea for all evils. It doesn't protect you from everything, as this story makes clear. But yes.
Another question I have related is about the estimation of the background. So when you're going for the new physics, I mean, how do you generate the background in a large volume of data to get the background estimate correct?
Well, so there's two approaches. Of course, you can use Monte Carlo, and we do that for, you know, if we know that a background is if we're worried about a very specific background, we will generate Monte Carlo. But what we try to do as far as possible is use data. So you look at control samples. You know that your background will be made up particularly of these sorts of decays. So you try and isolate those decays, or you isolate regions of data where you know your signal isn't. It's not true for all analyses, but that's certainly what we try to do, because there'll always be a question mark if you're reliant on Monte Carlo. Yeah.
Thanks.
Okay. Kajuridi. No, it's okay. The Zoom people would like to hear you.
No, while talking about the trigger, of course, he knows that there have been work from this institute for this LHCb level 1 trigger.
Yes.
For these long-lived particles based on GPU processes.
Yes, I should say
Bridge is present here.
Bridge here is actually made played a big role in actually getting this up and running. So if this works, we're still commissioning, so we shouldn't congratulate him yet because we're not actually taking worthwhile physics data. But if it does, then people like Bridge should deserve a lot of credit.
You know, you had this in JEPSI mass spectrum exotic state.
Yes.
Reported earlier. Now, do you have any exotic state in Epsilon by any chance?
No, we have not found LHCb. We can actually this plot would we can see this plot of the discoveries of hadrons at the LHC, because this isn't LHCb specifically, because this is here you can, this is the mass up here, right? So LHC, so yeah, in the epsilon. So these things have been discovered. These are not exotics though. This is I think this is a CMS discovery if I remember correctly. But these are hadronic final states, but there's no exotic state has been found yet at the LHC involving upsilons. The upsilons, of course, I mean, we expect this and we're looking, but these occur at a much lower rate than the J size. Sure.
Okay. Okay. TP?
Yeah, thank you for a very nice talk. So can one now rule out a fourth generation of quarks, or is that possibility still allowed by experiment?
Fourth generation of, well, there's various angles to this, but the angle we come to it from would be from this study of the unitarity triangle and checking that this triangle closes, and it closes to a large degree, but I guess you can never exclude the possibility that there always could be a fourth generation which couples to the other generations in a very weak manner, which would so I think that possibility is still on the cards, but it's not often discussed because it doesn't. I mean, who needs a fourth generation? We've know that there are three generations of light neutrinos. I mean, it could be wrong, but everything we see, it doesn't smell like there's a fourth generation.
Thank you. Thank you.
No, in this context, I want to make the comments that fourth generation quark for certain specific models are ruled out from the Higgs data. Okay, so at the LHC. So certain models, again, this is a vector sequential model and something like that. Those should be allowed. But from the Higgs data, certain models are just fourth generations are ruled out.
Right, yes. So,
there is a Higgs loop, it contributes in the Higgs production, the loop. It contributes the fourth generation quark. But from the Higgs measurement, those are disallowed.
Okay. Well, if there's one, yes, Gagan would like to.
Right. So, you know, that for this, some of the, that RK star, the fact turned out that, you know, sort of the particle misidentification kind of, that was not properly estimated, or with more data, with the better technique that got more precisely. So one would sort of go back and say this P5 prime, right? So from the experimental side, I mean, you know, of course it's a muon channel, but so, I mean, are we 100% sure there is the measurements that there is no possibility of any?
Well, one is never 100% sure, of course, but this is a much easier thing to measure with. It has very low backgrounds, and the thing is that this variable, I haven't defined it because you wouldn't appreciate the definition. It's very abstract, but it's constructed such that it is robust against form factor uncertainties, and is also has certain new physics sensitivities. But the beauty of it is that this variable, you can't associate, therefore you can't associate it with any particular region of the detector. any particular region of phase space. It's, you know, if you had a systematic problem, it would it's very difficult to conceive how such a problem would give you a local excess. And this measurement has been, and as I showed in the lectures, other experiments have measured this, though not with the same sensitivity. Okay, CMS had one point which is low, but all the other points from Atlas and from Bell also seem to be pointing in this direction. So this, I think the more likely explanation, if this is not new physics, is that there could be an issue with the theory. Yeah, so that is.
It's like RK star. Theoretically, it's very precise. So
Yeah,
that way.
yeah.
Okay.
Okay. Thank you.
Well, that concludes the colloquium. So thank you, Professor Wilkinson, once again for this wonderful presentation. And today you can join for tea. Thank you. All of you, please, you're welcome to the West Canteen.